Welcome to the presentation of our paper, Parallel Computation of Piecewise Linear Morse-Smale Segmentations, where we showcase an automatic segmentation algorithm that considers gradient flow behavior mimicking the behavior of the Morse-Smale complex while strongly scaling with more cores. In this paper, we want to compute a fast variant of the Morse-Smale complex. So the Morse-Smale complex itself is a data structure that allows you to segment a domain into regions of similar gradient flow. This means for any region you see on the image on the lower left side, if we are integrating upwards for any vertex, we will be reaching the same maximum. Also, if we will be integrating downwards for any vertex in the same region, we will be reaching the same minimum. Also, we have a complex structure that means that two neighboring regions share a common line. Also, we can either simplify the dataset before we compute the Morse-Smale complex, or we can simplify the Morse-Smale complex itself. The downsides of the Morse-Smale complex are that it is very slow to compute. Also, it introduces additional critical cells, especially in the border regions. And it can actually also miss some critical cells in border regions. Also, those border regions might not be segmented depending on the implementation. So now that we talked about the Morse-Smale complex, let's look at what the benefits of the Morse-Smale segmentation are and what its downsides are. So first of all, we get the full border segmentation, so the whole domain is segmented instead of just the center region with some border regions missing out. Also, we get all piecewise linear critical vertices, opposed to with the Morse-Smale complex, where we sometimes have additional ones at the border or even missing ones. Also, due to the algorithms chosen to compute the Morse-Smale segmentation, it is very fast to compute and works well in CPUs with multiple cores, so it has a great parallel efficiency. Sadly, we lose the complex structure, so we don't have all the neighboring information for all the cells here. And also, we can only simplify the dataset before computing the Morse-Smale segmentation, but currently it is not possible to simplify the Morse-Smale segmentation afterwards. Here we compare the Morse-Smale segmentation with the Morse-Smale complex. First, let us focus on the blue circled region. For the Morse-Smale segmentation, we find a maximum and a saddle on the border region, which is missing on the Morse-Smale complex. Also, when we look at the red circled region, we will find that part of the border is not segmented here, and also this border region degenerates into a line that goes towards the minimum. To compute the Morse-Smale segmentation, we take our input field and extract all extrema in there. After we have the extrema, we have to compute the ascending and descending segmentations. So to do this, we assign each vertex for the descending segmentation to its maximum in gradient direction. For the ascending segmentation, we assign every vertex to its minimum in inverted gradient direction. After we have both segmentations, we then combine them into the Morse-Smale segmentation by intersecting them. To compute the ascending and descending segmentation, the best way to speed up the computation time is path compression. Now, what we have to do is first, for the descending segmentation, we have to compute the gradient. And for the ascending segmentation, we have to compute the inverse gradient. Now we can proceed the same way for both fields. So now in each iteration, for each vertex, we apply it to its successor's successor. This way, we double the stack length in each iteration. And in log n steps, where n is the number of vertices from our vertex to a maximum or minimum, we get to the goal of assigning each vertex to its maximum or minimum. Now that we've seen how to generate the ascending and descending segmentation, and then Ultimately, by intersecting them, we're getting the Morse-Smale segmentation. We also want to generate geometry that separates those regions from each other, especially for 3D datasets. To do this, we use the marching tetrahedra or triangles algorithm. Here, we gave it two options. First, we have the region borders. For the region borders, every region gets its own border around them. So we have a hull surrounding that region, so we can color each hull by the ID of the region. Then on the other side, there are also the region boundaries. Here we can color each region by the intersection of two regions, so we can see where two regions intersect with those walls. For an example, let us look at the viscous fingering dataset modeling the mixing of a salt solution in water, forming so-called viscous fingers over time. Due to the implementation of the Morse-Smale segmentation, saddle-saddle separatrices are ignored while computing the segmentation. Compared to the Morse-Smale complex, this results in an easier segmentation and visualization, as saddle-saddle separatrices often clutter the image while being hard to remove from the Morse-Smale complex. So now, for performance analysis, let us compare our implementation to the one of the Topology Toolkit and the one of MSIR by Giulassi et al. First, the Miranda dataset that we're looking at is a time step of a Rayleigh-Taylor instability simulation. In this simulation, the border of a fuel cell capsule used for fusion burn is being simulated when heated by a laser. Small perturbations at the fuel cell border form and quickly grow, leading to a lot of critical points in the dataset. Regarding runtime efficiency, our implementation is over an order of magnitude faster than TTK and 5 to 7 times faster than MSIR. The speed-up factor and parallel efficiency plot show that our implementation scales much better with more cores. In this analysis, we also looked at the foot dataset at a resolution of 256 cubed, which is a CT scan of a human foot simplified to only exhibit one maxima for each bone. With this dataset, we achieved the speedup of over 50x over TTK and 40x over MSIR. Considering parallel efficiency, our implementation scales much better than the other two implementations. Now that we've seen how the Morse-Smale segmentation works and how it compares towards other algorithms that compute the Morse-Smale complex, let's quickly summarize. So first of all, the Morse-Smale segmentation allows us to get a full border segmentation compared to Morse-Smale complex implementations that sometimes don't segment the whole border. Also, Morse-Smale complex implementations can either exhibit additional critical cells or miss critical cells out. Then, like we just saw in the performance analysis, the Morse-Smale segmentation is much faster to compute compared to the Morse-Smale complex implementations. Also, our solution is open source and integrated in TTK 1.2.0. Thank you for your attention.